In a corner of the sky not far from the Swan, there is a blue so deep it seems to hold its breath. Astronomers call it HD 1189733b, but the name never captures the feeling. It is an exoplanet the size of Jupiter and the color of an ocean it does not possess. There are no seas here, no clouds of water, no soft rain. On this world, it rains liquid glass. The winds do not fall, they race. They push sideways across the face of the planet at nearly 9,000 kilometers an hour, shredding the idea of weather into something more like a constant. Silicate vapor condenses into droplets, microscopic beads of molten glass, then rides the jet stream like glitter trapped in a hurricane. Day never cools, night never rests. The orbit is a handcuff. One hemisphere faces its star forever. The headline writes itself, a planet where it rains glass. And behind it, a question that outlives the headline. What kind of chemistry makes a sky that cuts? What kind of physics paints a world the color of life and fills it with storms no life could bear? And, whispered because hope is a habit, could anything alien live there? The shock begins with expectation. Blue, in a planet, is a promise. Oceans, atmosphere, the familiar scatter of sunlight on air. Earth taught that association. HD 1189733b breaks it. Hubble's spectrographs measured the planet's reflected light and found a cobalt hue. But the blue comes not from water, but from silica-rich haze, tiny particles in the upper atmosphere that preferentially scatter blue wavelengths. A world can be the color of home and be nothing like it. Then the weather report arrives like a dare. Using high-resolution spectroscopy, astronomers watched the spectral fingerprint of sodium in the planet's atmosphere slide during transit, Doppler shifted by a jet stream. The speed, roughly 8,700 kilometers per hour, belongs on a data sheet for re-entry, not a sky. Wind at that scale turns precipitation into shrapnel. Here, rain is not gentle. It is motion under pressure. The concept of glass rain itself offends intuition until chemistry is allowed to speak. At the temperatures of a hot Jupiter's upper atmosphere, hundreds to more than 1,000 degrees Celsius, silicon and oxygen form vapor. On the cooler, darker night side and in rising, expanding air, that vapor can condense into silicate droplets like enstatite, MgSiO3, or forsterite, Mg2SiO4. With gravity as a guide and winds as a leash, droplets become rain. Not droplets of water, but of molten mineral. None of this was supposed to be easy to learn from 60 light-years away. That, perhaps, is the deepest shock, that a transit, a planet passing in front of its star, can give up this much. Light filters through a thin slice of atmosphere and carries clues in how it is absorbed and scattered. Einstein's mathematics lives here in the Doppler shift that reveals winds. Quantum mechanics lives in the exactness of absorption lines that betray atoms and molecules. The idea that a rainstorm can be inferred on another world is both audacious and now ordinary. The data story began in 2005, when HD 1189733b was confirmed as a transiting hot Jupiter, close enough and bright enough to become a laboratory. Spitzer watched its infrared glow, and by measuring the system's brightness as the planet slipped behind its star, a secondary eclipse, drew the first rough maps of temperature, dayside blistering, nightside less so, and a hot spot displaced eastward, evidence of a super-rotating equatorial jet. The planet does not just sit and cook, it moves its heat. Hubble's instruments, including STIS, peered in blue light and measured a geometric albedo that climbs at shorter wavelengths. The interpretation favored small particles suspended high in the atmosphere, Rayleigh-like scatterers, which is where silicate haze entered the conversation. Transmission spectra in the near-infrared weighed the atmosphere's contents as starlight filtered through. Water vapor signatures that wax and wane, muted by clouds. Sodium lines broad enough to announce both composition and motion. From the ground, spectrographs like HARPs and UVEs dissected the line profiles during transits. Tiny asymmetric shifts revealed wind. Not a breeze, the coherent push of an equatorial jet crossing the terminator, moving eastward from day to night. General circulation models, the same kind of physics used for Earth but tuned to tidal locking and intense irradiation, recovered that jet naturally. Heat on the day side creates pressure gradients. Rotation, slow in bulk, fast in local flow, stratification, and the balance of force produce a screaming current. Cloud microphysics filled in more of the picture. At certain pressures and temperatures, condensate curves for magnesium silicates bend downward, The night side and high-altitude day side intersect those curves. Nucleation theory says where droplets form, growth rates estimate sizes. My theory explains how those sizes scatter light. Droplets under these conditions are likely liquid or glassy, not crystalline, supercooled or molten depending on altitude and local heating. The portrait is not a single exposure. It is a stack, a color measured in blue light, a wind measured in spectral shifts, temperatures mapped in infrared, a cloud deck inferred from missing molecular features, and microphysics predicting a mineral rain. Together, they form a weather system in a place where weather should have been impossible to know. If the existence of glass rain is a surprise, its consequences are the real enigma. Clouds and hazes do not merely decorate a sky, they rewrite its energy budget. By reflecting starlight and trapping heat, silicate clouds can change day-night contrasts, shift wind speeds, and hide or reveal atmospheric chemistry. Observations of HD 1819733b have shown variability, features like sodium lines and water absorption that appear weaker or stronger depending on epoch, hinting at weather that changes, storms that wax and wane, cloud decks that rise and fall. It is a living system in the planet's star is active. Flares and spots complicate the light, injecting noise and, more importantly, high-energy radiation that breaks molecules apart. Photochemistry can build hazes from the fragments, coating silicate droplets in soot-like residues that further deepen the blue or mute it. In such a bath, chemistry never rests. It is driven, reset, and driven again. The glass rain is part of a cycle, a mineral cycle, where silicon evaporates, condenses, falls, and is lofted once more. Earth has a water cycle. This world has a rock cycle in the sky. Then there is escape. Observations in ultraviolet suggest that many hot Jupiters shed their outer layers. Stellar winds strip hydrogen and helium. The atmosphere becomes a cometary tail that glows briefly and vanishes into space. If HD 1899733b is bleeding mass, the upper air is a frontier where gravity and radiation fight. In that region, ions couple to magnetic fields. Currents may flow. Ohmic dissipation could heat deeper layers, altering temperatures all the way down to the condensation zones. The glass rain is no longer a local curiosity. It becomes linked to magnetism, escape, and the deep redistribution of heat. This is where the question about life earns its difficulty. Life as known requires gradients, differences that can be harnessed, and stability, environments that persist long enough for complexity to accumulate. HD 1819733b has gradients in abundance but stability in deficit. Winds tear any nascent structure apart. Radiation cracks molecules. Temperatures punish. Even speculations about cloud life, sometimes entertained for cooler worlds, meet their limits here. The droplets that drift are too hot, too sheared, too sparse in the chemistries that biology prefers. The mystery deepens because the more is learned, the more intertwined the effects appear. A color leads to a cloud leads to a jet leads to escape loops back to chemistry. No single measurement closes the loop. It remains open, dynamic, a system whose strangeness is a web, not a point. The leading picture binding these strands is coherent, but not complete. Tidal locking and irradiation. Locked rotation fixes a permanent day and night. Intense stellar heating drives a circulation pattern with a dominant eastward jet. That jet explains the offset hotspot and, critically, provides the conveyor belt that keeps the mineral cycle running. Vapor lofted on the day side, condensation initiated as air streams into the night. Silicate condensation and haze physics. At pressures near a millibar to a bar, temperature-pressure profiles intersect condensation curves for enstatite and forsterite. Homogeneous nucleation seeds droplets. Heterogeneous nucleation on photo-produced aerosols accelerates it. Droplet sizes in the submicron to few micron range produce the observed blue scattering. Whether those droplets are liquid or glassy depends on local temperature. Both regimes are plausible. As they grow, they fall, rain, until shear tears them apart, or they evaporate in warmer layers. Magnetohydrodynamic drag and ohmic heating. With partial ionization at high altitudes, winds interact with magnetic fields, generating currents that may deposit heat at depth. This alters the vertical temperature profile, changing where clouds can live. It also provides a pathway to explain inflated radii seen in many hot Jupiters, though HD 1899733b is not among the most inflated. Photochemical contributions. Stellar UV photons drive reactions that form complex hydrocarbons and nitriles, coating silicate droplets and adjusting their optical properties. These soots may be responsible for muted molecular features and for time-variable albedos. Each component is grounded in models or observations. Together, they make sense of the rain. Then come the edges. Speculations that test the limits but respect the data. Exotic droplet chemistry. Oxygen mixed into carbon-rich hazes might form silicon oxycarbide shells, materials with glass-like strength and altered refractive indices, changing scattering in ways that could mimic or mask silicate signals. Deep atmospheric seeding. Lightning in such a highly convective atmosphere could provide ionized pathways for nucleation, creating localized storms of glass rain, bands of enhanced precipitation moving with the jet. Life, if it is to be entertained at all, would likely not be biological in familiar terms. A realm of charged dust, sheared and ionized, suggests structures born of plasma physics, not biochemistry. Self-organizing filaments and vortices that store and release energy but do not evolve. Hawking's caution about the seductive power of simple analogies applies. Not everything that organizes is alive. A final model, less exotic but profound, ties it to Einstein. Winds and orbital motion shift spectral lines by kilometers per second, and only by accounting for relativity's strict bookkeeping, Doppler shifts, time dilation in fast flows, even subtle gravitational influences, do the measurements align. The same equations used to weigh galaxies steady a reading of weather on a blue-hot world. The search for alien life often rides on the back of headlines. A blue planet appears and the human mind runs ahead, filling it with oceans, clouds, coasts, and the sound of rain on roofs. HD 199733b gives that impulse something tender and then takes it away. The rain here does not soothe. It sears. The sky glitters, but it is not welcoming light. A lesson rests in that tension. Beauty is not a synonym for safety, and resemblance is not proof of kinship. Still, this world offers something more nourishing than fantasy. It offers scale. It shows a species how far its senses now reach. Instruments turn starlight into weather, wind speed into a shift in a sodium line, color into chemistry. There is humility in the method and audacity in the result. That is a kind of life, an intellectual ecosystem, thriving in observatories and code, in equations that cross the border from Earth to elsewhere without losing their footing. Einstein's ideas about light and motion whisper through every spectrum measured. The pulse of general circulation models, descendants of equations written for Earth's trade winds, beats in the jet that drives the glass. Hawking's career, anchored in the extremes of black holes, reminds that the edge cases are where physics clarifies itself. HD 199733b is not a singularity, but it is an edge case for weather. A place where rock becomes rain and wind becomes an engine. Do aliens live there? The honest answer is that, if alien means life as it is recognized, the conditions are hostile beyond metaphor. But the question does not fail when the answer is no. It succeeds, because it asks for a definition of life that is careful, and a definition of curiosity that is boundless. It turns attention to places where the answer might one day be yes, and to tools that can tell the difference. Somewhere tonight, that blue world will eclipse its star, and the light in a telescope will dip by a fraction. In that dip is a signature, and in that signature a sky. If glass falls there now, it will fall whether the minds here pay attention or not. Attention, then, is the choice. It is the only wealth that distance cannot dilute. Call to action, viewers who want more journeys into the strange familiar, worlds that look like home and feel like physics, can help this work continue. Liking the episode, sharing a thought in the comments, and subscribing for the next deep dive are small clicks that build big telescopes for ideas. And if a friend asks whether aliens live on the planet where it rains glass, there is a good answer to share. Not life as known, but a kind of truth that sharpens the meaning of life elsewhere. Wonder begins in the places where beauty and danger are the same.